Good morning. I hope you're doing all right. Sorry, I froze there for a second. All right. Good morning, everybody. So we are going to talk about interpreting graphs of position, velocity, and acceleration today. We are going to start talking about. We'll talk a little bit about calculus and the use of calculus when it comes to position, velocity, and acceleration. And if we have time, we're going to start talking about 2D kinematics, motion in two dimensions. Yeah, Holly notices my glasses. I should wear them more often. It's amazing how clear the world is. It's in HD. Maybe that's why I don't wear them more often, because everything is clearer. And Maggie saying scientists found sharks in an underwater volcano. And William says that wasn't on his 2020 bingo sheet. um, but before we start, let's take a look at Sakai quickly. And I just want to show you that I posted a week 2 motion lesson summary with links to areas of the textbook that you should be focusing on, links to slide decks, which all these slide decks are posted here in resources under slides and clicker questions. But I don't really like to use I don't like to use PowerPoints. I used to do a lot of PowerPoints, and then I did less and less and less, and now I do virtually no PowerPoint presentations. I find that they're you just kind of sit there and read what's on the slide, which you could do. But there's some nice pretty pictures in there if you check it out. And links to the WebAssign. So I haven't posted homework 2 yet, but I will before the end of the week. And on 2D kinematics. So there's a link to WebAssign there as well. But homework 1 is due at the end of this week. So please keep working on that. Okay, so there's a nice figure that's generated in the lab for this week, and let's take a look at that. That'll help motivate this discussion. Oh, I'm getting ahead of myself. Hold on a second. I meant the lab for next week. Okay. So you'll see this next week, not next week, in a couple weeks, on, this is week 4's lab actually, on Trinket.io, a VPython lab. But there's a simulation here which is helpful for our topic today. And I'm trying to get this so you can see it pretty well. Interesting. Zoom out a little bit. There we go. There, now I can click run. So this simulation is a ball that goes up and comes back down. And what you're seeing is the velocity vector in green and the acceleration vector in blue. And the velocity starts going up, then it gets small, and it changes direction and comes back down. All right, and the little red dots show where it was. But this simulation also generates these figures. Let me zoom out a little bit more. Here we go. Now I think we can see all three. Good. So this simulation also generates these 3 figures. And so there's a figure showing position as a function of time, velocity as a function of time, and acceleration as a function of time. So the ball goes up, reaches a maximum point, and then comes back down. Starts at 0, goes up to about, well, 100 and 30 meters at 5 seconds and then comes back down. Okay, so look at these graphs and what is the connection? So, all right, so a graph, when you're graphing mathematical quantities or graphing numerical quantities, the graph has features, and those features are its shape. At any given point, the graph has a value, and there's something on the horizontal axis, something on the vertical axis. Right, so you're plotting two physical quantities against each other. And so the question here is, what feature, what mathematical feature of the position versus time graph, the y position versus time graph, is related to the velocity versus time graph? So we'll go back here. So put your answer in the comments here. I'm saying, what feature of this graph, position versus time, is reflected in this graph, velocity versus time? Good, Holly. Holly's got it. It's the slope. It's the slope. So slope is rise over run. It's change in y over change in x. So up here you have slope that is positive. The function's increasing, but it's getting smaller. And then at the very top, the slope is 0. The line is flat. A tangent line would be flat. And then as you go down, the slope is negative. So you see that here. You got positive slope, 0. You cross 0, and now you have negative slope. So velocity versus time is the slope of position versus time. And in the same way, acceleration versus time is the slope of velocity versus time. The slope of this line is a constant. And you can see that down here. Okay. So, all right, so take a step forward, and then you guys know, or you will know after this semester in taking calculus, that the slope of a function, when you plot it, the slope of the function is mathematically the operation that we call the derivative. The derivative is something that exists at a point, or if you can calculate it at a point, is the slope of that line at that point. Okay. So in the language of calculus, velocity is the derivative of position with respect to time, and acceleration is the derivative of velocity with respect to time. But in perhaps more understandable language, if you haven't had calculus yet, what I'm saying is the velocity is the slope of position versus time. The acceleration is the slope of velocity versus time. Okay. And so that's a really important conceptual topic for this this unit, the connection between acceleration, velocity, and position when it comes to the graphical interpretation. So let's go to WebAssign here. And let's look at a problem that has you interpret. Okay, so problem 8 has you interpret this sketch of velocity versus time. And it says, well, if this is a velocity versus time graph for some thing undergoing motion in one dimension, what does its acceleration versus time graph look like? Okay, so let's just do this qualitatively first. All right, so qualitatively, what I mean is when you look at a graph, so this this velocity versus time graph is jagged. So we can look at each line segment and just say, well, is the slope positive, negative, or 0? And that will help us eliminate some of the options. this is blurry for you guys. Maybe I'll blow it up. Okay. Make it a little larger. So what we have here is from 0 to 20 seconds, velocity is increasing. That's positive slope. Then you have this point where it abruptly changes to negative from 20 to 50 seconds. And then the slope is 0 from 50 to 70 seconds. And then the slope is positive and then negative again. So we got positive, negative, 0, positive, negative. If we go down here, the other thing is the slope is constant on these intervals. So from 0 to 20, the slope is constant. It's not changing. And the slope is constant, constant and positive, constant and negative, constant and 0, constant and positive, constant and negative. So this option's out because acceleration is constant on these intervals, not changing. This option's out because you have constant accelerations, but you start with negative acceleration, and that's not what we're seeing here. We're seeing positive acceleration. So it's got to be one of these two. You have positive, negative, 0, positive, negative. Then it comes down to, well, they look exactly the same qualitatively. So you got to look at them and say, well, which one is the correct one quantitatively? And so let's just take the first interval here. How do we calculate the slope on this interval? Slope is change in y over change in x. In this case, change in velocity divided by change in time. So on this interval, from here to here, the change in velocity is 6 meters per second. You go from 0 to 6. And the change in time is 20 seconds. So the slope is 6 meters per second divided by 20 seconds. And where's my calculator? All right, let's see. 6 meters per second divided by 20 seconds gives me 0.3 meters per second, or meters per second squared. All right. So which one of these options has the slope, the acceleration being 0.3? Well, it's not this option. There it's more like 0.6. Here we go, 0.3. So it must be this one. And yay, okay. So let's go to the whiteboard. Now, Holly, I get to try out my new pen. All right. Moment of truth. Ooh, working pretty good. Slope of x versus t. Okay. So if I had an object and I plotted its position versus time and I got something like this, so we'll say this is 0 seconds, and this is 10 seconds, it's 0 meters, and this is 20 meters. And the question was, well, what's the slope of this line? Slope is change in whatever's on the y-axis divided by the change in what's ever on the x-axis. So maybe that's not the best way to say it here because x is on the y-axis, but I'm saying, you know, the convention is vertical is y-axis, horizontal is x-axis. So in this case, that would be change in x over change in time. So apparently, this new stylus has a button and I press it by accident and it turns into an eraser. Okay. So what is that? Well, the change in x here is 20 meters in 10 seconds. So that's 2 meters per second. You see that that is a velocity. It would be the average velocity over that interval of time. So if you did the same thing with v versus t, what you would find is the slope is a change in velocity with respect to time. That's an average acceleration. All right. Ooh. Oh, I can't make it any smaller. Okay, so where does this take us? Well, that's interesting. The slope thing moved. Wow, look at that. I can move things around. Didn't know that. Okay. So there's the connection here between slope and derivative is, what if you were to zoom in to an infinitesimally small part of this plot and said, what is the slope at that point? And that is the definition of the derivative. All right, that is, using the customary symbols, dx over dt. Okay, and so this is another way of saying that if you zoom in to a little tiny spot on this graph and say, what's the slope at that point, what you're calculating would be the instantaneous velocity at that point. All right, the average velocity is the slope over an interval. So if you shrink that down, remember we said the limit as delta t gets smaller and smaller and smaller. Graphically, that's asking what the slope is about an infinitesimally small segment of this plot. All right. And if you looked at a velocity versus time graph, you would see, in the limit where delta t gets really small, the slope goes to dv over dt, and that's the instantaneous acceleration. Okay. All right. So, wrong one. You guys who are taking calculus or have taken calculus 1, maybe they don't tell you this, but calculus was invented. Well, it was kind of invented by two people simultaneously and working in parallel. But one of the inventors was Sir Isaac Newton, and Sir Isaac Newton invented calculus to do physics. So calculus was the tool he invented to do physics. So he was thinking about problems like this. So it shouldn't be surprising that when you take calculus, a lot of the problems that you are given are physics-like problems. And let me give you an example. So there'll be a problem like there's a particle. It's always particles, because we encounter so many particles in everyday life. A particle whose position as a function of time, x position, so it's 1d, is 2x squared plus 3x minus 7. So what you're given is like this. If you think about it, this is so weird. You're like saying, well, there's a particle and its position as a function of time is like this, okay? And it's like a smooth line. It's a smooth line. It just follows a nice smooth line. How many particles do that in the real world? So problems like this are not so much about practicality in the real world as they are about understanding the conceptual connection between position and velocity when it comes to derivatives. And the question will be like, if this is its position, what is its velocity as a function of time? And so this becomes, well, okay, I know, velocity equals the derivative of x with respect to time. I messed up here already. Oop. Sorry, those are supposed to be t's. It's functions of t, not x. I got it right over there. And so I'm going to write the answer here. All right, I'm going to write the answer what it is. So when it comes to finding derivatives, in calculus you'll learn, there's a fundamental theorem for what a derivative is. And then if you follow what that derivative results in terms of certain kinds of functions, what you'll find is that for polynomials, which is what I've written down here, there's a nice, relatively easy to remember rule for learning about how you find the derivatives of polynomials. And I'm going to use that rule. And if this is my function, x, the derivative of that with respect to time gives me velocity, and it's going to be 4t plus 3. And why don't we just keep going? The acceleration then is the derivative of that with respect to time, the derivative of velocity, and that's going to equal 4. Okay, so if this is Greek to you, all right, what I recommend you do is watch that video I posted last week, an introduction to derivatives. Okay, hopefully, if you watch that, I think you'll get it. There's a rule that I'm applying here for finding the derivatives of polynomials, and if you watch that video, I think it'll be enough. All right. So check that out. Now, if you look at the homework here, where is it? I thought I gave you one. Yeah. So this problem right here, it says, the problem's giving you the acceleration as a function of time. And wow, it's a nice polynomial. Pt to the 6th power minus qt to the 7th power. And so p and q are constants. And you're asked to find the velocity as a function of time and the position as a function of time. Okay, and so what's going on here is if you work in one direction, position, taking the derivative of position gives you velocity. Taking the derivative of velocity gives you acceleration. Well, the inverse operation in calculus going the other way is the integral. Okay, and let's save the the graphical interpretation of the integral for another day. All right, because that's gonna, so the graphical interpretation of the derivative is the slope of a line at a point. All right, so that's what we talked about earlier. So we'll save the graphical interpretation of the integral for another day. But for this problem, and remember I said I'll make it extra credit for you guys. If you know what the acceleration is, the integral is applying this rule that I did over here for polynomials, and maybe you could figure it out. What I'm doing is I'm taking each coefficient, multiplying by the exponent of t, and then subtracting 1 from the exponent. So I get 2 times 2 is 4, and then subtract 1 from 2 and I get 1. And then 1 times 3 is 3, and subtract 1 from 1 I get 0. So that's why this is 4t plus 3, because t to the 0th power is 1. And then here there is no t. So the rule for integration is the reverse. What you do is you first add 1 to the exponent and then divide. So this would become p divided by 7 t to the 7th power minus q divided by 8 t to the 8th power. So I increase the exponents by 1 and divided by those exponents. And then I do that again. So this would be p divided by 7 times 8, 56, t to the 8th power, minus q divided by 7, or 8 times 9, t to the 9th power. All right, let's put one of these in and see if it's right. Let's put the position 1 in. If this one's right, the other one must be right. So I got p over 56 times t to the 8th power plus, minus q divided by, Holly, I'll get to your question in a second. Holly asked, well, what about the constant? So she knows something I'm glossing over here. Okay, so I got that right. So Holly's asking, what about the constant c? So what happens is that there's actually, if I was being careful, I would have to add some extra terms on here, and the reason is because there's, if you think about the graphical interpretation of derivative as the slope. Well, if I have a line that looks like this and I shift it up or down, I don't change its slope. So the derivative doesn't change if you vertically shift a function. So for a given derivative, there's actually an infinite number of functions that yield that derivative. They're just all basically vertical translations of the same function. And so that's why when you do the inverse operation, you typically have to add a constant to the result to represent that fact that you could shift the function up and down and still get the same derivative. Because remember, derivative is the shape, right? Not its position in absolute terms, but its shape. But in this case, they tell you initial velocity and position are 0. So with that knowledge, if x at 0 is 0, then those extra constants go away. All right, or let me say that another way. If v at time 0 is 0, that constant is 0. And if x at time 0 is 0, its constant is 0. All right. Right. So William says it's a definite integral. Yeah, that's how you can think about it too, in the sense that you have information that allows you to figure out what that constant is. All right. So I understand that if you haven't had calculus before, this is completely bewildering. All right. So let me say this as clearly as I can. The thing that I want you to know the most is that graphically, the interpretation of the slope of a position versus time graph is velocity, and the slope of a velocity versus time graph is acceleration. All right. Secondary to that, I want you to be able to do some calculus and to be able to perform some derivatives. And so watch that video that I posted last week. It's a more in-depth introduction to this topic. I'll tell you, share a story with you. When I was in high school, I took AP Physics in high school, and I was in a similar situation to some of you, where I was taking AP Physics at the same time I was taking AP Calculus, and the physics teacher taught us calculus at the same time we were learning why we needed to know it in physics class. And we learned derivatives in physics class before we learned derivatives in math class. Now, in the math class, we went into much more detail about the nature of derivatives in terms of the evolution of limit functions and things like that. So you get more in-depth knowledge. But it's a mathematical operation, just like multiplication or division, and it's just new. Okay. All right. So let's keep going. What was next? What was I going to do next? Some calculus. Okay. So I think I'll open this in a new window. On keyboard. Where are you, projectile? All right. So you'll see this again in a few weeks when you do the lab in a few weeks, the computational lab. But I end that lab with a link to this simulation, which is a much more elaborate simulation than the one that you will actually be helping to code in that lab in a couple weeks. But this is a simulation of well, if I make the cannon go straight up and click the launch button, erase, boom. Well, went off the screen. Here we go. What we have is a simulation of free fall when the cannon points straight up. So you have the cannonball go up. It does something funny at the top, and then it starts coming back down. All right. So let me ask you a question, and see if you can answer this in the comments. And the question is, at that point at the top of its path, what is its acceleration? So if you did the video vignette in the homework assignment, you're an expert on this, okay? What is the acceleration? Okay, William says negative 9.8. Negative 9.8. So William is assuming that down is negative, I'm guessing. And the acceleration is 9.8 meters per second downward. So that's correct. Okay. What's the acceleration? Let's launch it again. Wait, clear. Launch, pause. All right. I paused everything. Wait. You're not seeing this. Let's do this again. Ready, go. Fire. Oh. Launch. Okay. Let's try that again. Pause. All right, so I paused it. I'm not at the top. All right, play. Fire. Pause. Okay. So soon after the cannonball leaves the cannon, it's the tiniest little cannonball in the world. What's the acceleration at that moment in time? What's the acceleration? Nicole says positive 9.8. Positive 9.8. Okay, so Nicole is half right. Nicole is half right. Okay, so the part that you got right is the 9.8. 9.8, so good. Good job. At that moment in time, the cannonball is accelerating at 9.8 meters per second, but it's still accelerating downward. And you're like, what? But it's traveling upward. Yes, it is. but you got to keep those things separated in your mind. The fact that it's traveling upward is telling you that velocity is positive. All right, velocity is positive, but acceleration is negative. And the consequence of that is the cannonball is slowing down. It's slowing down. It's traveling upward, but accelerating downward. Those two vectors are anti-parallel. So at that moment in time, the acceleration is still negative 9.8 meters per second squared. What's the acceleration now? Negative 9.8. What's the acceleration now? Negative 9.8. What's the acceleration now? Negative 9.8. So, you see a pattern? For objects in free fall, the acceleration is always negative 9.8 meters per second squared. Always 9.8 meters per second, always pointing downward. Okay? Doesn't matter where the projectile is, whether it's moving up or moving down. If it's moving up, the consequence is it's slowing down. If it's moving down, the consequence is it's speeding up. All right. William, yes, we are forever subject to gravity. Well, near the Earth's surface. Okay, that's one of the simplifying assumptions here, is that we're near the Earth's surface. If we get really far away, then gravity starts to get weak. Okay, so now let's add a second dimension to this problem. And what I mean by that is, let's launch at an angle. Boom. Oh, I almost hit the target. Not quite. Okay. So here is the magic of projectile motion. You ready? So let me back up because I wasn't clear here. So what I just showed you is projectile motion. Let's watch it again. Boom. Maybe I can hit that target. Oh. Oh, yay, I got 2 stars. All right. So what we're watching here is projectile motion. We've launched a projectile. All right, so here's the magic of projectile motion. Projectile motion, so this magic is 2 parts. The first part is that you can take what's happening in 2 dimensions and break it into 1 dimensions. Okay, we can take what's happening in 2 dimensions and we can break it apart and say, well, okay, there's something happening in the vertical direction and then there's something happening in the horizontal direction. Okay, so that means that what we learned about taking vector quantities, velocities, accelerations, displacements, and thinking about them in terms of their x and y components is very important in when we're doing projectile motion. Okay, so one of the things about projectile motion that's magical is you can break it apart and look at the vertical component, the y component, and the x component separately. Okay, so we're gonna this magic is gonna pop into our lives later this semester too when it comes to forces and momentums, and so we will see this again. All right. The second thing about projectile motion is that what's happening vertically, up and down, is free fall. That's all it is, free fall. Okay? And what's happening horizontally is independent of that. Okay? So, let's, I got 10 minutes, that's good. I wonder if I can turn on, let's go back. Sorry, I keep, All right, I had the right one. All right, so I'm going to turn on the velocity vectors first. Okay, so you're seeing that this thing is speeding up, it's slowing down and then speeding up. On the way up, it's slowing down and then it's speeding up. All right, so here's a question for you, and put this in the. Holly says, let's see 3 stars. Okay. Oh, look at that, 3 stars. So my question for you is, one thing I noticed when I watched this that's different than free fall is if I threw a ball straight up in the air and then it comes back down, there's that moment in time when it reaches the top of its path when its velocity is 0. All right, when its velocity vector is 0. So if I were looking at that graphically, there'd be an arrow that goes away. It shrinks to nothing. And that's definitely not the case here with projectile motion. Watch again. I mean, the velocity vector gets shorter, but it never goes away. All right. All right, so when you're talking about projectile, it never comes to rest, not even momentarily. It never comes to rest at its peak. And the reason is because it's moving horizontally as well as vertically. So vertically, it comes to rest. It goes up and then momentarily stops before it starts coming back down. So vertically it comes to rest, but horizontally it never comes to rest. Well, until it lands, but then it's no longer a projectile. And what's happening horizontally, though, is it's always moving at a constant rate. So it's accelerating in the vertical direction, it's slowing down and then speeding up, but horizontally it's not accelerating. It's just traveling at a constant rate. All right, I can show you. I'll turn on the velocity vector. So now the velocity vector is yellow in the simulation, and the velocity vector is green. All right, the yellow is acceleration. Fire. Oh, I have air resistance on. Let's try that again. So you see the velocity vector is changing direction, but the acceleration vector is not. The acceleration vector is always pointing down, and it's always the same length. Because acceleration is always negative 9.8 meters per second squared. At the top, halfway down, and just after it's launched. All right. Okay, so the yeah, I think it's pretty rad too, Holly. The keys to projectile motion. Let's summarize them again. Okay, and we're gonna do tomorrow. Remember, no, not tomorrow. Friday. Remember that we're going to meet in person, and if you got to sign up using that sign up sheet on Sakai in the sidebar. And it's a recitation session, so we'll work on some problems that you have, or conceptual questions that you have. All right, that's my go-to. I'm going to ask you for questions first. All right, and if we have time during that recitation, I'll have the next homework assignment posted by that time. We can look at a problem-solving approach for projectile motion. If we don't have time, we'll do that on Monday. And shoot, what was I going to say? Anyway, so come to class on Friday if you're able, and if you want to, and if you get on the sign-up sheet ready to ask me questions about the homework. There's a homework assignment due Friday, which is one-dimensional motion. Okay. All right. So, but to summarize projectile motion, let's do this on the whiteboard. Oh, my computer went to sleep. Wakey, wake up. All right. Projectile motion. All right. And just draw a picture so we know what we're talking about. We're talking about a motion that follows a path like this. Mathematically, these are parabolas. That's such a horrible, that's really not that pretty. Yeah, that's about the same. Okay. Projectile motion is, we're going to take a 2D problem and we're going to break it into an X part and a Y part. And the things that we know are that, well, the Y part is, I'm going to use subscripts now, the acceleration in the Y direction is going to be 9.8 meters per second downward. The acceleration in the X direction is 0. Okay, so the vertical direction is free fall. Another way to say that is a sub y equals g. 9.8 meters per second squared. One thing that you guys, so this is a fundamental constant, and you might say, well, what makes it 9.8 meters per second squared? And actually, William earlier, I think, yeah, he put up 9.81 meters per second squared. And I said, well, why am I running to 9.8 instead of using 9.81? And I guess there's two answers. It's easier to remember and work with. But another answer is the acceleration due to gravity actually is slightly different at different points on the planet's surface. And this is because it's a consequence of the force of gravity, and the force of gravity is not constant. It's slightly different at different points on the surface of the Earth. All right, so 9.8 is a really good approximation of what this is. All right. Hey guys, I'm teaching. Go. Elliot, I'm teaching. Go. Go. Now.
Okay.
Sorry, my kids are bugging me. The other thing is that's going to help us here is this is my last question. I got a minute and a half. The question I have is, there is a physical quantity that connects these two sides. So what connects X and Y, vertical and horizontal? Here, watch this again. Boom. What physical quantity is the same for the vertical component of the motion and the horizontal component of the motion? And so there's really not that many physical quantities in our vocabulary right now. There's position, velocity, acceleration, and time. Position, velocity, acceleration, and time. So which one of those connects what's happening horizontally with the vertical? Maggie's got it. Good, Maggie. Time. So we just said the accelerations are different. The acceleration horizontally is 0. It's moving at a constant velocity horizontally. The acceleration vertically is negative 9.8 meters per second squared. And you look at this simulation, the velocity is definitely different. But the thing that connects the two is time. Okay, and that's really important, because when it comes to solving problems, if we know how long the projectile is moving vertically, we know how long it was moving horizontally as well. So time is the glue that holds, let me say this is like, here, this is, I'll say it as philosophically as I can. Ready? Time is the glue that binds the dimensions of space together. Time binds X and Y together. All right, I will see some of you on Friday. We're not doing a live stream on Friday. All right, it's in person in Bird Science 110. All right, so work on your homework, and if you guys have questions or want to meet in the office hours, send me an email and we'll set up a time. All right, have a nice day.